Hello, my name is Mark, and so welcome to a series of tutorials where I introduce Dagster. That is a parallel open source SAT solver. So this is a series of 4 tutorials which I'm sharing with you now. So particularly this particular tool that I'm introducing called Dagster, we're going to walk through it, what it does, how it works, how to use it. Feel free to contact me, there is my email address, and as Dagster is a software that is open source, there is the GitHub link. We make note that in these tutorials I will be referring to Python, so that's potentially a prerequisite. But yes, let's begin. So the first thing is, what we're going to do in this tutorial is we're going to talk about what a SAT problem is, and specifically the problem that Dagster is designed to solve. And in this tutorial we're going to talk about the primary means, generally speaking, by which SAT problems are solved. That is specific backtracking search or conflict-driven clause learning. Alternatively, stochastic local search or SLS are primary paradigms of solving SAT problems. In the consequent tutorials we will actually introduce the components of Dagster, how Dagster is used, and also how Dagster's source is organized, with examples and case studies along the way. So, beginning tutorial 1, Dagster solves SAT problems. So, what is a SAT problem? So, a satisfiability problem, or a SAT problem, is a constraint programming problem, where we have a set of binary variables, so for instance x1 all the way up to xn, and we have a set of constraints that those binary variables should satisfy. So this set of constraints needs to be mutually satisfied, and they are often represented in a conjunctive normal form, or CNF, which is a conjunction, that is an AND, over a disjunction, that is a OR, of variables or their negations, that is their literals. So for instance, an example of a set of constraints, so we have 2 constraints for variable values x1, x2, and x3. So for instance, the first constraint, x1 or not x2. So that is the constraint that either x1 must be true or x2 must be false. And a second constraint, not x2 or x3. That is the constraint that x2 must be false or x3 must be true. And this is an example of conjunctive normal form, right? We have a conjunction over disjunctions. And this is often represented in the computer in terms of a CNF file. So for instance, down there below we have a CNF file represent of these 2 clauses. So a clause is a constraint in this context. So PCNF, 3 variables, 2 clauses. So there's the header, and then the first constraint is 1 space minus 2 0. That is the constraint of x1 being true or x2 must be false, and a postpen 0, and which is a termination of the clause. And the second constraint, not 2 or 3, is the second clause in the CNF file. So this is a SAT problem, and this is how it's represented in a computer. So let's take an example of a SAT problem. So like I enjoy Sudoku puzzles, so this here is an example of a Sudoku puzzle. And we're going to show how, basically, using SAT, we can model a Sudoku problem as a SAT problem. But like we'll get to it, but there are many examples of things that you could model using SAT. But okay, so let's take an example. So Sudoku is a puzzle, if you haven't come across it before, where you have to fill in a grid of numbers. So for each box in the grid, you need to put one number between 1 and 9, such that there is exactly one of each number in every row of the grid, in every column of the grid, and in every 3x3 subgrid. So the Sudoku puzzle is made up of 9 3x3 subgrids, like so. And at the beginning of the puzzle you have a set of clues, or that is boxes that are already filled in, and you have to fill in the rest of the boxes to satisfy all of the constraints, such that there is only one number in each row, column, and box. And there's only one way to do that, and that's the puzzle. So what we can do, so in this example, Sudoku, so we can have, say, binary variables corresponding to the filling of specific digits in specific boxes. and then consequently we can represent those constraints. So using a bit of mathematical notation, so we have a Boolean xijv, if and only if number v is in square ij. I is row, j is column, whatever. And consequently, so those are the variables in the problem, we can model the constraints. So for instance, like one example of a constraint is if there is a number in a square, then any other number is not in a square, right? So for all I, j, and pairs of numbers v and v prime, where v and v prime are distinct, if xijv, then not xijv prime, and vice versa. So that's represented. So and over all ij and v prime not equal v, not xijv or not xijv prime, right? That is, if there is one number in there, if there is one number in a particular square, then there is no other number in that particular square. Now, another example of a constraint is that not only can there not be two or more numbers in a square, but there must at least be one number in the square for it to be a solution, right? So that is for all I and j, xijv for some v must be true. So and over ij, because we have one constraint for every ij, and then we have or xijv over all the v. So so this is like xij v equals 1, or xij v equals 2, or xij v equals 3, all the way up to 9. One of those must be true to make that or statement true. So these are two examples of minimal constraints. There must be one number in a square and not more than one, right? Now additionally, we have the rules of Sudoku. So specifically, each row in each column has every number, right? So this is for all v, for all values v, and for all columns j. The row I must have a value v. So and over v and j, and then for each v and j, you have the or over I of xijv. So for instance, this is like x row is equal to 1, jv, or x row is equal to 2, jv, or x row is equal to 3, jv. So this is like for every row, there must exist, for every column and value, there must exist the value v. And then we have the vice versa for the row and the column. And then we also have the constraint that for every box, that is for every 3x3 subgrid of the Sudoku puzzle, there must exist every number as well. And these constraints are sufficient to encode the Sudoku problem, right? Because we have all of the constraints, we have to fill in exactly one number in each box, and every row and column and subgrid must have all of the numbers. And consequently, this is sufficient. Now what we can do, these are the constraints that go into coding a Sudoku puzzle. So what we can do is we can create a script that outputs a CNF file corresponding to these constraints. So particularly we can do this in Python, because Python is a relatively easy language to do this with. Let me walk you through it. So for instance, like we have d equals 3 is the size of the subgrid, that is the smaller grid. And then we have the actual total grid dimension, which is d times d, which is 9 by 9, right? So Sudoku puzzles are 9 by 9 box, and they're made up of 3 by 3 subgrids. And then we have CLS is the array that holds the clauses that we're about to populate on line 3. And then what we do is we have, so in this case, a lambda function, right? Which is basically, if you pass in the row, the column, and the value, it will then return the index of the Boolean variable that corresponds to that. So this is like x RCV is a variable, a binary variable, say index number 5, for instance. And that's just the formula that gives you a unique index for every RC and V, where RC and V range from 1 to 9. So anyway, so this is the setup. So what we do, given that setup, we begin to encode the constraints, right? So as before, so we take a look at the constraints. So the first one is if there is a number in the square, there's not, then any other number is not, and there must at least be one number in every square. So let's consider that as the first thing. So the first one is for all R and all C. So this is for every box in the Sudoku puzzle. we have the following constraints. So the cell at RC has at least one value, right? So this is the big, so CLS, that is the set of clauses, dot append, we're adding a clause, and then, so this is iterating over R and C, and then for every V, we have a clause, that is an array, variable RCV for V in range 1 to 9, inclusive. So that is, so the cell at least must have one of every value. So variable RC1, that where V is 1, or variable RC2, or variable RC3, or variable RC4, all the way up to 9, one of those must be true. That is, so we're appending the clause that is the OR of those valuations. Right, that is the, let's turn back to it. So that is the second constraint here. There is at least one of each number in it. There is at least one number in a square. Cool. And then the second constraint, the cell at RC has at most one value. Right, this is particularly the constraint that if there is one value in the square, there is not another. So what we have, iterating over R and C, that is for each square. So what we do is we have an iteration over possible values. So for each value in range 1 to 9, and for each W that's not equal to V, we have clause.append minus RCV minus RCW. Right, so this is the implication that if variable RCV is true, then variable RCW must be false, and vice versa. So this is the constraint, the secondary constraint, that there is only one, there is at most one of each value in the cell. And so that is the sum total of the first two constraints of the Sudoku puzzle, right? And then now we need to encode the second two constraints, right? That is the constraint that for every row and column has to have one of every number, and each box has one of every number. So let's do this. So for each value in range 1 to 9, n plus 1, so we have the constraints. So each row has the value v, right? So for row in range 1 to 9, the column in for C in range 1 to 9, that is the column index of that row, RCV, and then we have RCV for some V must be true. So variable RCV for the range C in the row R for the value V must be true. One of those variables must be true. So this is, so let's say R is 1 and V is 1. So variable R111 or R121, R131, R141, etc. So this is, the value must be in the first row. That one of the first rows must have the value V in it. And then we have the reverse thing for the columns. So for C in range 1 to 9 inclusive, and then we have an iteration of the row index. So variable RCV must be true for some R of that respective column. And then we have it's a little bit more involved, but the exact same thing except for each subgrid. So for subgrid index in 0 to D, that is R and C, X and Y, and then we have R in range 1 to D plus 1, and it's essentially the same thing. I mean, you can bore over it if you want, but basically this is the entire encoding of the constraints of the Sudoku puzzle. Each row has the value V, each column has the value V, and each subgrid has the value V. Anyway, so once we do that, so we have the constraints set up that each cell has at most one value and exactly one value, and then we have each row has a value V, each column has a value V, each subgrid has a value V. And then what we need to do is we need to add the clues or the unit constraints that correspond with the filled-in digits of the puzzle. So, for instance, like if there is a constraint of the puzzle that, you know, row 1, column 1 has a value 5, then we're appending a unitary constraint that says our solution must satisfy that. And we append that for all of the clues or the given numbers in the puzzle. And then finally, we output the CNF file. So print just prints the standard out. The header, that is p_cnf, and then we output the number of variables, which in this case is 9 by 9 by 9. that is one variable for each value, column and row, and then the length of the clauses, the number of clauses. And then for each clause in the clause, we just print with a postpen 0. And so basically we can do that, and this generates a CNF corresponding to a Sudoku puzzle. And then consequently, using this script, we can code any Sudoku puzzle we like. Perhaps even having different size Sudoku puzzles, like maybe we change the value D or whatever. Anyway, so what we do, so we throw this Python script sudoku.py, we say Python sudoku.py, and then we pipe the standard output to, say, su.cnf. And then once we have a CNF file, we can basically solve that using any SAT solver that you like. So in this tutorial series, we will introduce Dagster as a tool for solving these SAT problems, but for this example, we can use a simple off-the-shelf, old-fashioned solver called MiniSat, for instance, or Ling, or there's a whole bunch of them. So we say MiniSat, and then we give it the CNF file, su.cnf, and then we also give it the output file that we want to spit the output to, so su_output.txt, and if we run that, and then consequently we take a look at that output, the output will say it is SAT, it is satisfiable, that all of the clauses that you gave it can be mutually satisfied, and these are the values that satisfied the problem. So for instance, in this case, the variable 1 is false, the variable 2 is false, the variable 3 is false, the variable 4 is false, the variable 5 is true, the variable 6 is false, the variable 7, blah, 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 blah. And those are the valuations that satisfy the Sudoku problem, coincidentally. Consequently, like when, this is all of the values of the binary variables, but, we can use those values to then, actually formulate what the actual Sudoku solution was, right? Because this is not human friendly. So for instance, we can make a little tiny Python script like this, which just reads the output and then reformulates that as integers in squares. And then we can actually see the Sudoku solution. Right, so for instance, like this here is the 9x9 filled in Sudoku problem, coincidentally with the value 5 in square 1, 1. And we can see that in every row, there is the values 1, 2, 3, 4, 5, 6, 7, 8, 9. And then conversely, in every column, 1, 2, 3, 4, 5, 6, 7, 8, 9. And in every subgrid, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because every 3x3 subgrid of the problem uniquely has the values 1 to 9. And congratulations, we have just solved a Sudoku puzzle using SAT, which is kind of nice. Now, Sudoku is just an example because there's several puzzle Sudoku YouTube channels that I like to follow, so I'm a bit of a Sudoku fan. But there are many other kinds of problems that you can encode as SAT and also solve in SAT. So basically, in a very pure sense, right, like problems where there are variables that can be formulated or represented or approximated in a discrete form that could be rendered in binary form can be, in principle, encoded as SAT problem. So this is a very wide range of problems. So particularly, for instance, software model checking. That is like, reasoning about the particular parts of execution through a software problem. Is something that you can reason about using SAT and model. So this is particularly bounded model checking. In the subsequent tutorials, we'll talk a little bit about that. But there are other problems as well. So for instance, like mathematical problems. So, in this tutorial series, we'll talk a little bit about the Costas array problem, which is an example of a combinatorial mathematical problem that you can, in principle, solve using SAT. But there's other examples as well. So for instance, like planning problems. So model checking we've already mentioned, but there's also like resource assignment problems of, like what worker should do what job in what environment. Perhaps you could do scheduling or planning problems. Like there's a whole range of different things that you could, in principle, encode in SAT and then consequently use SAT solvers to solve. So Dagster is, the object of this tutorial series, and it is an example of a SAT solver, particularly a parallel open source SAT solver. Okay, so talking about what a SAT problem is sort of gets, interesting. It's like, okay, so we can model all these problems and we can pass them into some known SAT solvers. But there's the question of, okay, well, in the broader sense, how do you solve a SAT problem? And you'll appreciate that this has been a problem that a lot of people have put a lot of mental effort into over the decades. But there are kind of emerged essentially two fundamental processes of solving SAT. I mean, there are others, but these are primary ones, most well known. So the first one is a systematic process called backtracking. So we're going to get into that. So let's take an example SAT problem. So this is an example of a CNF file of 6 variables and 8 clauses. So the first clause is the constraint that variable 1 must be true, or variable 2 must be true, or variable 3 must be true. The second constraint is variable 3 must be true, or variable 4 must be true, or variable 5 must be true, except and so on and so on. So this is an example of a SAT problem that I just made up. And then now we're going to solve it using a particular process, and I want to just break it down for you. All right, so the first one is just what I would say is just like a very, very primitive backtracking search process. So in this case, we have the variable values 1, 2, 3, 4, 5, and 6. And then on the left-hand side, we've got all of the clauses. So 1, 2, 3, 3, 4, 5, 5, 6, minus 3, minus 5, etc., etc. And those are our clauses. Now, we begin the state with all of the variables, that is the variables 1 to 6, not having assigned values true or false, right? And if all of the variables are not assigned a true or false, then, trivially, none of the clauses are satisfied or unsatisfied, right? I mean, because they can't be. So the first thing we do is we choose a variable and we give it a value. So let's say we choose the variable number 1 and we give it the value true. So, on the right-hand side here, we have variable 1 is true, and then I've just put N for unassigned, neutral, whatever, and colored it aqua, right? So variable 1 is 2, variable true is neutral, unassigned. Now, because we have assigned variable 1 to be true, what that has done is it has immediately, straight out of the gate, satisfied some of the clauses. So clause number 1, that is 1 is 2, or 2 is true, or 3 is true, is now a clause that is completely satisfied because 1 is true. 1 is true, or 2 is true, or 3 is true, is now true because 1 is true. And likewise, 1 is 2, or 2 is true, or 4 is true, is now satisfied because 1 is true. Right? So what we've done is we've highlighted the clause blue, and we've highlighted the variable that made the clause satisfied as a slightly lighter shade of blue. All right? So that's the first assignment. And then now we can proceed by choosing another variable and assigning it another value. So why not? Let's assign 2 to be true. Now, when we assigned 2 to be true, so now 1 is 2 and 2 is true by this step, and all the rest of the variable values are unassigned, what's happened is that assigning variable 2 to be true hasn't satisfied any other clauses. So there's no other clauses that were satisfied previously that are now made satisfied by assigning variable 2 to be true. What it has done is that there are now some clauses where they are closer to being unsatisfied because variable 2 was assigned to be true, right? So this clause here, 2 is false, or 3 is true, or 4 is false, right? Now, because variable 2 is true, that first clause has made, that first variable, literal, has been falsified, which makes this clause a little bit tighter, right? So it is now more difficult to make this clause satisfied because now we have to choose variables 3 to be true or 4 to be false to make that clause satisfied, if that makes sense. So I've highlighted that violation, which is not quite a violation, almost, as being in red. All right. So let us proceed with making another variable assignment because we might as well. So in this case, because we might as well just choose, let's say 3 is true. And because we assign 3 to be true, there are some other clauses that now are made satisfied. So particularly, like the variable that was almost unsatisfied last time, because 2 was false, because 2 was assigned to be true and we had not true in one of the clauses. Now, because 3 is true, this clause here is actually now satisfied, right? It becomes blue. It's like, woohoo, right? And because we've assigned 3 to be true, then some other clauses also become satisfied. So, for instance, this second clause here, 3 is true, or 4 is true, or 5 is true, is now true because 3 is true. Additionally, we note that the first clause here, 1 is 2 or 2 is true or 3 is true is now triply satisfied because all of the variables coincide. But we note that this clause here, 3 is false or 5 is false, is now pretty difficult to satisfy because 3 is true, right? And it's highlighted red. So let us proceed with assigning another variable. Because we're on 1, 2, 3, let's go 4. So let's assign 4 to be true, because why not? Now that doesn't do a lot in terms of the clauses that actually end up satisfied. It highlights one red because it's not actually particularly helpful. It doesn't satisfy any clauses that weren't already satisfied, and it makes the clauses that were unsatisfied or close to being unsatisfied more close to be unsatisfied. Anyway, let's just keep going. So let's assign, we've got 1, 2, 3, 4, and we might as well just go 5. Let's assign 5 to be true. Now, when we do assign 5 to be true, what we notice here is we've got a clause that is now positively unsatisfied. It is false. It's a real issue, right? So because we've assigned variable 3 to be true and variable 5 to be true, the clause, the constraint, that 3 is false or 5 is false is now positively violated, right? And in the business we call this a contradiction, right? We've reached an error state. And so the basic idea in the backtracking search is that we revert the change, so it's a contradiction, we revert the change and we make a different choice. Right? So now instead of assigning 5 to be true, we go back and we assign 5 to be false. Now if we do that, there are some clauses that results in a different configuration of clauses being satisfied and unsatisfied, but we aren't in a contradiction anymore. So it is possible for variables 1, 2, 3, 4, and 5, so 1, 2, 3, and 4 to be true and 5 to be false yet. Okay, and then, all right, we might as well proceed in, say, assigning variable number 6. So if we assign variable number 6 to be true, we have another contradiction, right? Because there is a constraint there, which is 4 is false or 5 is true or 6 is false. And that is now satisfied because 4 is true and 5 is false and 6 is true. So that's a contradiction, which then forces us to make a different decision of assigning 6 to be negative. So right. Now, if we do that, we get another contradiction. Right, so, because now the clause 5 is true or 6 is true is now false, because 5 is false and 6 is false. So we get another contradiction, right? So what we're doing is we're going down this little rabbit hole, and we're encountering contradictions. And when we encounter a contradiction, it triggers us to backtrack and make a different choice. So because we've reached a point where we've got double contradictions, right? If we have 1, 2, 3, and 4 being true, 5 and false, right, then it doesn't matter which way we assign variable number 6, we get a contradiction. Right, so we need to double backtrack, right? So we know that if we go 1, 2, 3, 4, and then we assign 5 to be false, we get a contradiction either way on 6. So we must be 1, 2, 3, 4, and then we have now a double contradiction on 5. Right? So 5, if we assign it true or false, will result in a contradiction either way we go. So we backtrack yet again, and then make a different choice. So in this case, now we're assigning 4 to be false. All right. So then, assigning 4 to be false, we can do that. It doesn't unsatisfy any clauses. And then, going as we again, we choose value 5 to be true, and that results in a contradiction, which means we assign 5 to be false, which then is possible. And then we assign 6 to be true, and congratulations, we just solved the whole problem. Right, now this is just a very basic backtracking variable assignment process, which has some degree of historical. But you can appreciate that this is sort of a systematic way of going about solving a problem. Right, you're sort of making variable assignments, and then you're making sequential variable assignments until you get a contradiction whereby you backtrack and make a different choice. And using this process, you can see that we can basically scan all over, all of the possible variable choices. And if there's a solution, we'll find it, and if there's not, then we'll get a contradiction at level 1, and that will prove that there is no solutions to this thing. So it's very systematic. So features of backtracking search: it's systematic and complete. Either it will find a solution, or if it doesn't find a solution, then we know that there is no solution to be found. Right? And the other one is, when we were doing this search process, where you could have made different variable selections. So in the previous example, we went 1, 2, 3, 4, 5 in terms of variables, but we didn't need to do that. And in fact, different variable choices actually do yield very different search qualities. So if you have a bad variable selection, that can make the whole process remarkably longer. Or if you have a short variable selection, a very appropriate one, it can make the search process much better. But now this is just the elements of what is basic backtracking search. But since then, there's been a lot of additional engineering hacks and features, and a lot of research and a lot of development on this process. Right. So one of the things we're going to talk about is we're going to talk about implications and clause learning, which is major advance on this process. So let's start with the basic one, and that is implication. So in the previous scenario, when we were doing backtracking search, so there were each of the clauses at any point in the search could be represented as being one of 4 different cases. Right. So the first one is when a clause is satisfied. Right. So like if we have a clause not 2 or 3 or not 4, and 3 is true and 4 is false, then the clause is satisfied, and that's a great thing. We want more of that, right? Alternatively, the clause can be entirely unsatisfied. That is a contradiction. So for instance, if the clause not 2 or 3 or not 4, if 2 was true and 3 was false and 4 was true, that would be a full violation of that constraint, that clause, which would then trigger us to do a backtrack. But there is, 2 subcases as well, right? So the clause can be not yet unsatisfied or satisfied by more than one variable. So for instance, like if we had the clause not 2 or 3 or not 4, and 2 and 4 were unassigned variables, but 3 was assigned to be false, right? Then that clause, not 2 or 3 or not 4, could yet be made satisfied by assigning the variables 2 or 4 to their respective values. But there's another important case where the clause is unsatisfied by one variable, right? That is, so for instance, if we had the clause not 2 or 3 or not 4, and we had 2 being true and 3 being false, then the only way to make that clause actually satisfied in consequent search is to assign the value 4 to be negative, to be false, right? So that last case is kind of interesting, right? So if in our search we had a clause that was unsatisfied but for one variable, then we would know that to make that clause satisfied, we would have to assign that variable one way, right? So in this case, the variable 4 being false would be forced in a subsequent search to make that clause satisfied, which is kind of interesting, right? Because if we ever encounter this situation, we can say, okay, next variable selection, not 4, right? So for instance, what we can do is we can actually build that into the backtracking search. Right. So for instance, if we have a situation where there is a clause but for one variable being unsatisfied, then we can directly force that valuation. We don't need to do the branching factor on that. So and we can notice here, we're going to run the same process again. We're going to notice that with this process, which is called implication, what happens is that it makes the search much faster. And furthermore, a sequence of implications can chain together. So for instance, if we take the same problem as last time, we say, all right, let's assign variable 1 to be true. That satisfies various clauses on the left-hand side there. Great, okay, we don't have any implications. So let's assign variable 2 to be true. Same thing as we did last time. No worries here. Let's assign variable 3 to be true. Now, at this point, we have an interesting situation. So, right, now what we notice is we have the clause, the variable 3 is false or variable 5 is false, but in our assignments, we have assigned variable 3 to be true. And that means that the only way that that clause can become satisfied is if variable 5 is consequently assigned to be false. Right? Now, if we do that, which should be the next step, which, what will happen is that will then impact on this upper clause here, right? Because if we consequently assign variable 5 to be false, then the clause 5 or 6, that will then consequently become the same thing, right? Because variable 5 will be false. That means that variable 6 must be true, right? Which will then mean that this clause down here, that is the last remaining unsatisfied clause, not 4 or 5 or 6, right? Because variable 5 is now assigned to be false and variable 6 is now assigned to be true by the implications that we've done, then variable not 4 must be true. All right, all right, let's do this. So what we do is we have 1, 2, and 3, and then that setting 3 gives us an implication chain for not 5 and not 6. And then that gives us then an implication chain for not 4. Right, and if we do that, bam, we've reached a solution. So what happened there is that we just completely bypassed this branching, methodical, backtracking, contradicting search just by following the implications. Right, so once we did variables 1, 2, and 3 assigned to be true, true, and true, then we had implications on 5, implication on 6, and then implication on 4, which then satisfied our problem immediately, right? Which was very, very quick. So there's no backtracking hocus pocus once we hit this point. So this is like a sequence of implications that can actually chain together to yield a true solution to the problem, which is quite powerful. And this was sort of, core process in DPLL, which is the historic backtracking search to solve SAT. Now, the other one to note is that implications don't necessarily chain together to create a true solution to the problem. So the implications can lead to contradiction. So we'll go through this. So this is the exact same problem as last time, except I've added an additional clause, not 2 or not 3 or 4 or not 6. So this is just a slight modification. And now, if we do the same process, we go variable 1 is 2, variable 2 is true, variable 3 is true, and now we get the implication chain on 5 and 6 and 4. But that will then contradict with this clause that I've added, deliberately added, to give us a contradiction. So, boom, 5 and 6 implied, and now we have a problem here, right? Because implication-wise, we have implication on not 4, and we have implication on 4, right? So if we have 2 problems. Either way we go, if we follow the implication chain to assign 4 to be negative, we should also follow the implication chain to assign 4 as positive. So either way we go here, we've got a contradiction. So what happens is we have a backtracking search where we assign variables different values, one at a time, and then we have a process that is implication. That is, when we get to a sufficient point where we've assigned variables, then the remaining unsatisfied variables in each of the clauses, if they are unitary, are then consequently forced, and that leads to a chain of forcings which can lead to either true solution to the problem or contradiction. And obviously, if we have a chain of implications that leads to a contradiction, then necessarily we have to backtrack and make a different choice, right? Because it's part of the backtracking search. Now, the other one is that implications are one of those things that you can have a chain of implications that can be triggered at multiple points in the process, right? So in the previous example, we started by assigning variable 1 to be true, variable 2 to be true, variable 3 to be true, and then implication, 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 contradiction. Now what happens is we're going to trigger the same implication, except instead of assigning variable 1 to be true at the outset, we're going to assign variable 1 to be false at the outset. So for instance, variable 1 being false, variable 2 being true, variable 3 being true, and then we hit upon the same implication chain. Variable 3 being true implies variable 5 is false, variable 5 implies variable 6 is true, variable 5 is false, variable 6 is true implies variable 4 is false, but contradiction because variable 2 being true, variable 3 being true, variable 6 being true implies positive 4. Contradiction. So between these two examples, we have 1 false, 2 true, 3 true, contradiction. And in the previous example, 1 true, 2 true, 3 true, implication, contradiction. So the same implication chain to a contradiction is triggered multiple times. And now the next thing is clause learning. So implication chains can lead to contradiction, and they can do so multiple ways throughout the search process. And one way of averting this problem is to add additional clauses that are logically redundant to the problem to block the implication chains that leads to a contradiction. So this will, save us time and effort in the future. Once we encounter an implication chain once, then we add a clause to prevent the occurrence of the implication chain again in the future, right? Because we don't want to reason over the same logic over and over and over again. So one of the things we can do is we draw this thing called an implication graph, or an I-graph, right? So this is the exact I-graph of the chain that we came across before. If we assign variable 3 to be true, then that implies that 5 is false, and 5 is false implies that 6 is true, and 5 is false and 6 is true implies that 4 is false. 3 is false, 3 is true and 6 is true implies that, together with 2 being true, implies that 4 is true. And we have a contradiction on 4, right? Because that implication chain means that 4 is false and 4 is true, which is contradicting. So one of the things we can do is we can assign a cut in this graph, right, to prevent the implication occurring. So the first and foremost is we could cut the graph across that red line here, right? So for instance, we could say, okay, so we're going to add a clause that is not 2 or not 3 or not 6 or 5, right? So that's an additional clause that would cut the implication chain or prevent the implication contradiction from occurring at that point. Additionally, we could cut the implication chain here. So that is, we add a clause that would prevent this implication chain from occurring to the contradiction. That is, the variable 2 must be false, or variable 3 must be false, or variable 5 must be true, right? Or, more logically, we'd probably add the implication clause here, right? So we add the clause that variable 2 must be false, or variable 3 must be false, right? And if variable 2 is false or 3 is false, then that would prevent the implication chain to the contradiction that we just saw. So, in this case, let us proceed with adding the clause not 2 or not 3 as a learnt clause to the problem. So, for instance, we have the same problem as last time. We had the clause that I added previously just to make the problem harder. And then we have the occurrence of the learnt clause, not 2 or not 3. And, as we will go through, we can show that this is actually a more powerful problem. So, for instance, if we assign variable 1 to be true, variable 2 to be true, then, boom, we have an implication chain that completely avoids the previous implication chain to a contradiction that coincidentally satisfies the problem. So let's go through this. Right, so if we have variable 1 to be true and variable 3 to be true, then because of our learnt clause, we now know that variable 3 must be false. Right, because if variable 3 was not false, then we would have the exact same implication chain as we had before that would lead to a contradiction. So variable 3 must be false. And if variable 3 is false, then implies variable 4 is false. Right, and if variable 4 is false, then variable 3 is false and variable 4 is false, and variable 6 is false, and so on and so on and so on. We've got a whole chain of implications, and that chain of implications satisfies the problem outright. So what happened is in the previous runs of the problem, we encountered a chain of implications that led to a contradiction. We analyzed the set of implications as a graph. We cut the graph to add a learnt clause, and with the learnt clause, the problem becomes more powerful, and we get a solution faster. So this is the process of learnt clause learning, right? And is characteristic of what's called conflict-driven clause learning process. Now, it's a major innovation in stat solving, and there's more to it than that. But so basically, one of the things is that there's different ways, as I alluded to previously, of making a cut in the implication graph to get different learnt clauses. There is actually additional different variable learnt selection rules that include clause learning. So there's a notably famous one called VSIDS, which prioritizes the variables that occur in the learnt clauses that are learnt. Right. So if a variable occurs frequently in the learnt clauses, then it must be an important variable, and we want to assign that. And then there's the other one is that over time, like each of the additional clauses that are learnt, the learnt clauses, over time they can become redundant or stale. Like sometimes a learnt clause is only valuable for the first, so many points of the program solution process, and these things over time can accumulate. So there's actually clause forgetting processes because each of the learnt clauses are logically redundant. Adding them to the problem doesn't result in a stronger problem or a different problem. It's just redundant clauses. So you can actually forget clauses over time, which can be advantageous. And the other one is that there's different policies on what's called restarting, right? So, if you've done a search to a point where you've learnt a whole bunch of learnt clauses, you can restart the whole process from scratch and make different variable selections. Anyway, so there's a whole bunch of configuration on CDCL solvers, and particularly these different kinds of options and different algorithmic choices, different variable selection rules, clause forgetting policies, they're made manifest in a whole range of different SAT solvers that are out there. So, particularly, Minisat is a relatively famous one. There's another one that we use called Ling Ling. There's another one that Dagster itself is based off called TinySat. And I think, like every so many years, there's a SAT solving competition, right, where, different academics around the world get together and kind of, see who can make the biggest, fastest SAT solver using some combination of these things and others. Any case, right, so this is CDCL solving. So we're going to summary and a little break. So I'm just going to go over, so a SAT problem is a problem of binary variables with constraints that those binary variables must satisfy. They are often represented in conjunctive normal form, or CNF, is defined by clauses that are ORs, or binary of literals. And the primary way of solving SAT problems is with a backtracking search. Historically DPLL, currently CDCL is the acronym these things go by. That systematically scans through the search space of binary decisions or binary assignments. Most notably, choosing binary assignments leads to implication chains, and these implication chains can lead to true solutions or can lead to contradictions, which then trigger a backtrack. And implication chains can be broken by adding learnt clauses to the problem process, right? And these learnt clauses, what they do is they improve the SAT solving process, because implication chains can be triggered multiple ways. And furthermore, those learnt clauses can build off each other to make the solution process much, much faster. All right, so that's just a little break. So if you want to go get yourself a coffee or something, probably be advisable if you drink coffee. Anyway, so now that's where we're up to. So the next thing I'm going to do is I'm going to introduce you briefly to a completely different way of solving SAT problem. So the next way of solving a SAT problem is called stochastic local search. And it's an entirely different process from the backtracking search that I've introduced. Basically, what it does is it begins by assigning all of the binary variables a value, and what it does is it flips the values of the binary variables to increase the number of satisfied clauses in various ways. So some people like to view this as sort of like an optimization, hill climbing kind of a thing, and if that's the way you like to visualize it, then cool. So what we're going to do is we're going to take an example problem. So this is basically the same problem as we had before. So we have, the same set of clauses, and then the clause that I added previously to make it harder, and then we have, just for good measure, the logically redundant learnt clause in there from the conflict-driven clause learning. Now, in this case, we have a random assignments of our initial variables. So variable 1 is false, variable 2 is true, variable 3 is true, variable 4 is false, variable 5 is true, variable 6 is true. This is just a random. Anyway, so that's where we begin. And that configuration of assignments for those variables makes some of the clauses satisfied and some of the clauses unsatisfied. Right? So because variable 3 is true and variable 5 is true, the clause, not 3 or 5, that is this constraint here, is unsatisfied because of that assignment, and so forth and so on. Now, what we can do is in the SLS processes, we choose a variable and then we flip its value. Right? So let's say we take variable 2 and we flip its value from being true to be false. All right. Now that will make some clauses unsatisfied and some clauses satisfied. So, for instance, the clause variable 1 is true, or variable 2 is true, or variable 4 is true, now becomes unsatisfied because we flipped variable 1 from being true to being false. All right, so that's highlighted in red there. We've got like one clause that was satisfied that is now unsatisfied by flipping the value of variable 2. But we also have other clauses that were unsatisfied that now become satisfied because we flipped the value of variable 2. So, for instance, the last clause here, 2 is false or 3 is false, becomes satisfied now that 2 is actually false. So we can choose another variable. Let's say variable number 1, and we can flip the variable number 1, and that will result in some changes to the clauses being satisfied. And then we can proceed like this. So one of the most basic and boring ways of doing this is to, to calculate at each stage, like would, by flipping this variable, I increase the number of clauses that are satisfied, and if so, then I flip it. Or, choose the maximum variable that would increase the number of variables, the number of clauses that would be satisfied. So we flip variable 2, we flip variable 1, we flip variable 5, and then congratulations, we solved the problem. Now, I think you can appreciate that this is perhaps a little bit less systematic than the backtracking searches that we explored previously, and that is true. Now, one of the things that can happen in this stochastic local process, because we're just choosing a variable and flipping its value according to some logic, what can happen is that we have a situation sometimes emergent where we have the flips can occur in a circle. So, for instance, if we take the same problem and say if we flip variable value 2 and if we flip value 4, what we can do is we flip variable value 5 and we flip it again and we flip it, and then 6, and we flip 6, flip 6, flip 6, flip 6. And then each time, we're going around in circles, right? That this stochastic variable flipping process can sort of eat its own tail in an algorithmic sense. Flipping variables without actually ever managing to satisfy all of the clauses in the problem. And this is probably one of the major drawbacks of stochastic local search. So, anyway, so on and so on forever. Now, the SLS process, the stochastic local search, is an entirely different process to the backtracking search, the CDCL that we've just explored. And one of the major drawbacks of the SLS process is that it can actually lead to an infinite loop. So, there are ways to sort of more or less escape this tendency to kind of sort of get trapped in a local maxima of trying to increasingly satisfy the variables but not being able to satisfy all of them. So, for instance, like we can add a complete randomization step where it just chooses a variable at random and flips it, or we can introduce, say, like a full restart, right, where we just, at some point in the row we say, okay, we've, reached a likely, loop. We're just going to do a full random restart all of the variable values. Another way we can go about it is, there's, so for instance, called a taboo, where basically we kind of keep track of the set of recent variable assignments that we've just seen, and then we add like a way of remembering where the search has been, and then we force the search to not repeat itself, like a self-avoiding walk. Another way of sort of throwing a spanner in the works is to essentially to it's called dynamic clause weighting. Is essentially to, over time, increasingly prioritizes clauses that are perpetually unsatisfied, but that won't necessarily solve the thing. But there's lots of stuff that we can do to the SLS process to make it more competitive. But there are some just major differences in terms of paradigm between backtracking search and stochastic local search. So particularly, only the conflict-driven clause learning, the backtracking search, can actually generate a full unsat. Right, so if you throw an unsat problem into a SLS process, it'll never finish, guaranteed. Right, because it can never reach the point where it can reason that there are no solutions, because all it's done is just hill climbing. And the other one is, like in that context, only a CDCL can guarantee that it will finish. That is either return a solution or return unsat. And the other one is, and this is kind of borne out by experience, is that backtracking search such as CDCL and stochastic local search are basically, they're better at different classes of SAT problem. So, in some problems, stochastic local search will likely be better, and in some cases, the conflict-driven clause learning will likely actually be a genuinely better way of solving the problem. So there's broad differences between SLS and CDCL in terms of practice. So, summary conclusion. SAT problems are binary constraint satisfaction problems. The constraints are represented in conjunctive normal form, defined as a binary OR over literals for each clause, and those clauses must be satisfied. The clauses are constraints. And, in the context of SAT problems, there are at least two broad ways of solving them, particularly, so conflict-driven clause learning, DPLL, is a backtracking systematic search that scans through the space of the binary decisions. Those decisions lead to implication chains, which can be broken by adding learnt clauses, and learnt clauses build on each other to accelerate the solving process. And additional to the backtracking search, there is an entirely different search approach called stochastic local search, which is a non-systematic search and has its own advantages and disadvantages. Particularly, it is adept at different kinds of problems. Additionally, it has a weakness, that is, it can get stuck in local maxima, and it doesn't necessarily finish, and it can't generate unsat proofs, but it can be faster at particular problems. So this is the end of tutorial number 1. Feel free to join us for tutorial number 2, and thank you.